Hi, and welcome to the Water Research Foundation webcast, Retrofit and Management of Metallic Pipe with Cathodic Protection. My name is Jian Zhang. I'm a research manager with the foundation, and I will be the moderator for today's webcast. So this webcast will present results from the Foundation Project 4618, which was co-funded by Tarrant Regional Water District in Texas. The report has been published, so here is the link for our subscribers to download. Now I'd like to introduce today's presenters. Our first presenter is Dr. Graham Bell. Graham is a Senior Vice President and HDR's Business Class Director for Condition Assessment and Rehabilitation. Graham has more than 38 years of experience in condition assessment of civil engineering structures, as well as designing and testing of corrosion control facilities. He is past chair of the AWWA Corrosion Control Committee and various technical committees for NACE International. Graham is certified by NACE International as both a corrosion and cathodic protection specialist and has provided services to utilities throughout the United States. Our second speaker is Dr. Masade Akunan. She is a corrosion engineer and assistant project manager with HDR. She has over 12 years of experience in condition assessment and rehabilitation of metallic and reinforced concrete infrastructures. She received her doctoral degree in corrosion engineering from the University of South Florida. She currently serves as the vice chair of the NACE San Diego section. So before I turn this over to Graham, I want to remind the audience that there will be a Q&A session after the presentation. You can type your questions on the webcast webpage either during or after the presentation. We will answer as many questions as time permits. And if there are any questions that we don't have time to get to, we will email answers to people who ask the questions. And this webcast should be available for download from our website by tomorrow. And lastly, it's important for us to hear from you regarding today's webcast. So before you leave, there will be a post-event survey. Please take the survey. With that, Graham.
Thank you very much, Jan. And I appreciate the opportunity to talk to you about this project, which is a follow-on to a project I was involved with about 15 years ago, but it's a logical advancement of that. And when we started out this project, we had certain expectations, and along the way, we worked through those expectations to the reality. And it turned out to be a very good project and provides a lot of valuable information. So. A little bit of an agenda for what we're going to talk about today. You've had the introduction. We'll have an introduction and background. We'll talk about the two forms of cathodic protection that were being applied in order to extend the life of metallic pipe in the ground. One is hotspot protection and retrofit cathodic protection. We'll cover case studies that give examples of how this works, and talk about the modeling and economics. And one of the things about this report and the previous report that we did is we really try and provide a best practice manual or information that can be directly used by the utility, people within the utilities, to actually implement what we talk about. These our projects are intended to be very utility friendly, very applicable, more applied science than fundamental science. And at the end, there'll be a summary, and we have about 36 to 40 minutes of presentation material, and we try to leave plenty of time for questions and answers, because we find that that's the most valuable part. So with that, that's what we're going to cover today. And the acknowledgments: these projects are extremely interactive and integrated, and they can be a bit of a nightmare to administer, particularly when you have this many participants. We had over 17 utilities, large and small. We had cathodic protection vendors. We had NACE International, the Corrosion Society. We had small engineering companies that really brought together, a big cross section of what goes on with corrosion and cathodic protection in the overall in the industry. And obviously, my role as the PI and then the co-PIs involved in this were greatly helped by Mercedes, who you're going to hear from, and Addison Smith from HDR, who helped do a lot of the legwork. And Steve Poole was also very involved in really administering the contract and making sure that everything got done, the communication was there. And so there was a whole team that comes in behind this, and we couldn't have done it without our two sub-consultants from Colorado State University, Dr. Neil Gregg. Dr. Gregg has been involved in the water utility industry for a long time and really helped out bring a very down-to-earth utility experience. And Dr. Balvant Rajani from Rajani Consultants would help to bring in the Canadian experience, because in many ways the Canadian utilities are further ahead on the application of cathodic protection to extend the life of metallic pipes in the ground. Then overseeing the whole thing is Jan Zhang from the Research Foundation as a PM, but also the input from the Project Advisory Committee, Jeff Ahn, Dale Clausen, and Andrew Hughes, which are actually were able to give us, again, more of that utility influence. So it's a very practical project with a lot of moving parts, and I hope that you find these as valuable as many of the participants did. So in the upper right-hand corner, you'll see a reference to the chapters of the report. When they're highlighted in green, that means that's what we are talking about out there. So just keep in mind that as we go through. So really, one of the findings that we like to bring out is overall, what's the motivation for these projects, or this project in particular, and that is really that corrosion, the external corrosion in particular of water mains, is a very expensive proposition. When you look at it from the total cost to societal cost, it's about 3.4% of the GDP of a country overall. And when you look at the drinking water and sewer systems, it's about $36 billion. So it's a very large problem, and this was addressed in one of the earlier reports that I was involved with back. This is previous to the change of Water Research Foundation in its name. This is back when it was American Water Works Association Research Foundation, but still very valuable report that first gave some of the foundational information for this particular project. And it was a 3-year project, and we had a very detailed literature survey. We did utility survey, we did laboratory testing, we developed what we refer to as the corrosion control master plan, which sort of gives you the outline of how, if you want to implement a corrosion control program, how you can start. So this particular project report was the foundation, and you'll see in a few minutes how it really showed up. And really, and that was project 2608, and what we found back even then, back in I think 2004, it was published, so it's 14 years ago, that even though cathodic protection has been known since basically 1831 to be a way to prevent corrosion, and it's used extensively in the oil and gas industry, it really hasn't caught on that much in the water utility industry, and that question was why, and we have some reasons why we'll talk about here. And we also recognize that the water utility industry has a unique perspective on corrosion and corrosion control, because they're not regulatorily, there's no regulatory requirement. In the oil and gas industry, if people don't apply cathodic protection or improperly apply it, somebody will go to jail. So this and the other thing about the water utility industry is that in the oil and gas industry, you only have one pipe material. You have steel pipe with a fusion bonded epoxy, but in the water industry, we have concrete pipe, we have pre-stressed pipe, we have steel pipe, cast iron, ductile iron. So that changes a bit how you're going to approach corrosion control and the application of cathodic protection. But the reason we're talking about this 2608 report is one of the main participants that we spent a lot of time with and got a lot of good information was really with Louisville Water Company, and there was a gentleman there who was very interested in understanding the data and information about pipe leaks, pipe breaks, etc. And this is one of his graphs that showed that for pipe failures, it showed that that they're able to show that that if you look at the difference between breaks and leaks, a break is something where it's typically a circular break or a longitudinal break, a large hole in it. A leak is something where water is squirting out through a corrosion hole on the outside. And they realized that about over 75% of their leaks were probably preventable. The breaks couldn't be prevented with the application of cathodic protection, but the leaks could. So they undertook a program on a particular series of pipes. In an area, the DeMelle Avenue area, in a 2004 project, and you'll see that it says cumulative number of breaks on the left there. You see the bars are going along, and you see at 0 there, it shows that they started applying cathodic protection. Went down and did a retrofit project in that particular area. And what it shows is that red line rolls over. So they basically had a couple leaks after they applied cathodic protection, and since then they haven't had any. If they hadn't installed the cathodic protection, they would have followed that blue line going up, having more and more leaks, more and more unpreventable. So it showed in this particular area that cathodic protection worked, but the real point was that it took them almost 4 to 5 years before they were able to see the value of implementing it. And so their persistence and patience in the application and the tracking of the data really helped them to understand what was going on within their system and eventually to reduce the amount of breaks. So that was all part of this 2608 project, and then that last graph I showed, actually I came across in 2014, and so it was relatively new, but it showed that what we've been talking about in 2608 was on the mark. So what we came up with, there are really 4 outcomes from 2608, and then eventually this new project we're going to talk about as part of it is really you have to pay attention, assess the condition of your pipe, understand the data, track the data in order for you to give yourself the information that you need in order to go forward and make and improve the situation you're in. And if you ignore it, it doesn't do any good. If you ignore it, the problem only gets worse. That's a result of the second law of thermodynamics. You have to take action. You have to just go out and just do it. This is back. I know we stole that line from the folks at Nike, but the problem is people don't know where to start. But the advantage with cathodic protection in particular is you can't do any harm with it. It's very hard, particularly with galvanic, to do any harm, but you just got to go out and do things. But you also have to commit to a future, because it's going to take a few years for what you're doing to really show up. So with that, I'm going to turn the presentation over to Mercedes, let her talk about what was 4618, this new project that took forward those concepts that we developed in 2608. So without further ado, I'll turn it over to her to explain what we did in 4618. Mercedes, it's all yours.
Yes, Thank you so much, Dr. Bell. So the next slide, we are talking about the Water Research Foundation 4618 project objectives. So as you may know, water utilities can choose to do nothing to mitigate external corrosion, but motivating factors are typically to provide uninterrupted water service and high-quality water supply to customers. Some utilities have been exploring techniques to fight external corrosion, but a standard and defensible approach does not exist. Therefore, the goal of this project was to produce a utility-focused design criteria, standard specification, drawings, and financial models that illustrate the benefits of anode retrofit and hot spotting programs. We are hoping that this manual is equally useful to a technician at a small utility and management at a major utility. So, Water Research Foundation 4618 project approach. As Dr. Bell mentioned, our approach was built on the foundation of previous research and the information that we gathered from the utilities in United States and Canada. On the right side, you see the U.S. case studies that was gathered by Dr. Neil Greek from Colorado State University, and also the Canadian case study that was gathered by Dr. Rajani. Along with literature review and case studies, we also conducted 2 workshops that I'm going to go over with. Based on the information that we gathered from these utilities and workshops, we developed engineering best practices and financial templates that we're going to discuss next. So literature review. A quick interesting thing about the literature search that we did for this project was that there are many, many online publications and resources out there specifically for cathodic protection of pipelines. But when we look closely, only 1% of those online publications are regarding cathodic protection of water pipelines. So therefore, because of this limited available online resources, it was very important to conduct workshops and case studies and surveys. So as part of this project, we conducted 2 workshops. The first workshop was at NACE Corrosion Annual Conference 2016 in Vancouver, Canada, and our audience were mainly corrosion professionals. The second workshop was at AWWA ACE 2016 in Chicago, and our audience were mainly water professionals. The objectives of this workshop was to provide notification of the project, discuss the benefit and challenges of cathodic protection, specifically on water systems, present and gather case studies, and more importantly, to collect information and professional perspectives. During this workshop, we noticed a very important difference in perspectives. When talking to corrosion engineers, they all thought that cathodic protection always worked, the cost can always be justified, and then they would get into the detail of design parameters, monitoring, and protection criteria. And we understood that the corrosion engineer's job is just to stop corrosion, and they're 100% committed to corrosion and corrosion control. But when we were talking to water professionals and water utilities, there were so many uncertainties about cathodic protection. And there were so many questions. They were unclear if cathodic protection will work on their system, how long and how much money has to be spent to see the effect, how to justify the cost and budget for it, where to start, is it going to be simple enough to incorporate through routine operations, how to maintain it, and who's going to be in charge of it, and what to do with the collected data. So we understood that the water utilities job is to deliver water, and corrosion is among many other things that they have to worry about. This difference in perspective was very important because it helped us to shape our manual and make it more utility friendly and make it more utility focused. During the surveys and workshops, we were told about major challenges in implication of cathodic protection for water pipelines. The main challenges included the lack of awareness on primary cause of failures in aging structures, the lack of industry standards for CP application on water systems, and lack of proper communication between utility division, for example, engineering and distribution division, lack of financial models showing the benefit of CP, and many utilities are dealing with limited resources for crew training. There was some confusion by competing messages from experts, not knowing where to start, and being afraid of unknowns were main challenges that we were told of. So the conclusion from all these case studies and qualitative case studies and workshop and survey was that no one size fits all. It exists for cathodic protection for the water line. With the variety in the pipe characteristics, soils and environment, and other risk factors, there should be customized approaches when you want to launch your CP for your utility. With that, we get to the main items of this report, which are hot spotting and retrofitting. And as Dr. Bell mentioned, those are included on the right top part that you see in Chapter 7 and 2. We discuss about this. Before we get into the hot spot and retrofitting, a quick refresher on cathodic protection. So cathodic protection, as you may know, is one of the 4 methods of controlling corrosion. The other 3 methods are shown on the right. It is an electrochemical method, and the basic concept behind it is by feeding electrons or current to metallic components, the metal ion's tendency to separate from the metal, usually in form of oxide, is reduced, resulting in a smaller metal loss. This current can come from oxidation of a sacrificial anode, such as in galvanic system, or from an AC source or a rectifier in case of an impressed current system. It is not black magic, and it's not new to water utilities. It's been around for a long time. And there are commonly used guidelines, such as NACE International Standards, that talks about the design parameters and criteria for cathodic protection. So with that, what is the anode hot spotting? So anode hot spotting is referred to as opportunistic installation of cathodic protection anodes at the breakage repair. So basically what we are asking is that install anode every time you excavate for a routine repair. We ask your crew to have the anodes in the back of their truck, and as they're excavating to conduct their repairs, they install the anode at the same time. The procedure is easy and relatively quick. It's not labor intensive, and the cost is insignificant to the cost of excavation. Typically, an anode costs about $200, and an average cost of an excavation is about $5,000. So it's insignificant cost. So all we are asking is that there's no monitoring involved. You install the anode and can forget about it, but you want to keep record of the location just in case in future you want to go back and use more sophisticated cathodic protection system. In that case, you would like to know the location of existing anodes. So the anode hot spotting is going to delay the future break, and it stabilizes the overall rate of break. So we expect that in a relatively short time, you would see a stabilization of the overall rate break, but it may take longer time to see a reduction with hot spotting. On the right side, you see anode installation using cat welding on a pipe as part of a routine repair. So the next slide is about anode retrofit. What is anode retrofit? Basically, anode retrofit refers to systematic installation of anodes at each pipe segment. So it can be done in 2 ways: either install an anode on each pipe segment using keyhole techniques, or excavate every other joint, bind the joint, and install the anode. On the right side, unfortunately I don't have a pointer to show, but on the top it shows the anode retrofit, and in the bottom shows the traditional cathodic protection. For traditional cathodic protection, you will have to make sure that every segment of pipe is electrically bonded and continuous. However, in anode retrofit, you can only excavate every other joint and bond them and install the anode. It will require some labor training and resources, and requires maintenance for long-time effectiveness. So the cost is, of course, more expensive than hot spotting, and can typically be justified as capital improvement project cost. The hot spotting will stop the breaks and reduce the overall rate of breaks. It will take some time to see the full effect, but it's going to be effective in long term. As you see on the picture, the bottom, you see some keyholing being done and the excavation for this anode retrofit. As part of our report, we provided sample specifications and sample drawings for anode installation. For example, in this slide, you will see the two common methods of installation of anode wire to the pipe using pin brazing and cat welding. These procedures are relatively simple to apply and require minimum training. So now let's discuss pros and cons of hot spotting, which seems like a no-brainer. So hot spotting is just a small increase in maintenance cost. As I discussed, is only the cost of anode is about $200 or so, and can be utilized on electrically discontinuous pipe. As you know, main concern with the water pipelines is electrical continuity, and hot spotting can be definitely applied on electrically discontinuous pipe. It can be utilized in localized problematic areas, and it will stabilize the number of breaks. It can be incorporated in an O&M cost, making it easy to implement between the maintenance crew and the lower management. It does not require the thorough knowledge of corrosion or CP design. It could be a good starting point for smaller size utilities with limited resources. Simply, as I said, keep the anode in the back of the truck and install it as part of the routine pipe repair. Prepackaged anodes and installation tools are not expensive, and anode installation is a simple procedure and does not require extensive training. There is no limit as where it can be applied. Let's talk about some items that can be considered as disadvantage of hot spotting. Of course, when you compare hot spotting with a full-scale cathodic protection, then economic analysis may give the method undue advantage, assuming the higher level of CP effectiveness. It may take 6 to 10 years transition period to show a significant breakage reduction. As I mentioned earlier, the purpose of hot spotting is to stabilize the overall break rate, but it may take longer to see a significant breakage reduction. A long-time transition period may lead to abandoning the program. Bulk purchases in anode might be beneficial, but the storage and damage could increase the cost of the anode. And one more important thing is that when you do minimal engineering and planning, you shouldn't expect a perfect result. So it may not result in a perfect protection, and the protection may not be as effective as long-lasting as a fully designed system. However, hot spotting will provide some protection even for a short time in almost all cases. So now that we talk about hot spotting and anode retrofit, let's discuss the direct application of cathodic protection for water pipelines. For new installation, we certainly recommend that water utilities go refer back to the Water Research Foundation 2608 that Dr. Bell discussed earlier on. For those new installations, we certainly recommend that it should be fully designed, the pipeline should be fully electrically continuous, and the monitoring and maintenance system should be installed. However, for existing pipelines, which are likely not electrically continuous and establishing electrical continuity would be expensive, a full-scale CP cost may be hard to justify, and the utilities may not have the trained crew and resources to monitor and maintain, and some utilities don't even know where to start. Then we certainly recommend that you consider hot spotting and retrofitting as this project discusses. With that, we're going to be moving on to the case studies. These are only selected case studies that are presented here, and you can find more case studies in Chapter 5 and 6 and Chapter 2 of our report, but we only selected few here for presentation. The first case study is one of the first case studies that shows the successful application of cathodic protection on water pipelines. This is related to East Bay Municipal Utility District, East Bay MUD, and their Mokelumne Aqueduct that was built in 1928. The aqueduct consists of 93 miles of pipe, 81 miles of it being steel, and 70 miles of it being buried in variety of soils, rocks, very corrosive to non-corrosive. The first cathodic protection system was launched in 1934. The expected life for the pipelines without CP was 70 years. Actually, this was a very special case study because Mr. Mark Lewis from Mr. Mark presented this at our workshop, and he was very, very passionate about this project. Here in this slide on the right, you see a graph that shows the overall breaks and the years for this aqueduct. At the beginning, after installation, they had a sharp increase in number of leaks, and then in 1934 they start applying the cathodic protection. As you know, back then in 1934, the anodes weren't as efficient as today, and you know, they were basically burying a giant piece of steel as anode in the ground. However, as you see, after application of even first type of CPs, you see a reduction in breaks and a stabilization in overall breaks. And then after every time they interrupted their system to build a new addition or new cross connection, they had an increasing number of breaks and a slowdown after they restored their CP system. So this is a great evidence for 30 years of successful application of CP on their system and extension of the life for this aqueduct. The second case study that I'm going to cover is from Des Moines Water Works. They have a lot of snowfall, an average of 35 inches, and their soil is very corrosive, and they had high rates of breaks, 0.4 breaks per miles per year for their 747 miles of metallic pipes. They started launching their cathodic protection system in 2004, and in the graph on the right, you see the red dots where are the number of breaks and projection of breaks for the pipeline with no cathodic protection, and the blue dots show after they install and launch their CP program in 2004. Their conclusion from their CP analysis and CP program was that the anode retrofit program resulted in 90% reduction in breaks at a cost of less than 10% of their replacement. The third case study that we're going to cover is from City of Calgary. City of Calgary has over 3,000 miles of potable water pipe, and they started their hot spotting program in 1973 and their retrofit program in 1998. As you see in the graph on the right, the blue line shows the number of breaks, and the x-axis shows the year, and the yellow and the red columns show the main replacement and anode retrofit programs. As you see, after 1998 that they launched their retrofit program, there is a sharp decrease in the overall number of breaks. And their conclusion from their program was that anode retrofit on appropriate pipe candidates is 1/10 of the cost of the replacement and extend the life of the pipe in 30-year intervals. So if you are interested in these case studies, specifically the Canadian case studies, Dr. Rajani conducted more comprehensive analysis, statistical analysis, and computational modeling for these case studies, and those are included in the same chapter. I would like to mention two of these graphs because I would think this is a good illustration of the effectiveness of hot spotting and retrofit program. The graph on the bottom left shows that hot spotting was applied somewhere between 1980s and 1990s for this utility. And as you see, you can see the overall rate stabilizes after hot spotting was launched. On the figure on the right, you see that the retrofit was applied in 1999, and there is a decrease in overall reduction. There's a decrease in overall break rates for this utility. With that, we're going to be moving on to the modeling and economics that we conducted for this research. So what is our approach for numerical and financial models that you see in this report? So there were already existing published data that shows the equations and functions for simplified failure rate projections. we basically took these functions and revised them to incorporate the effect of CP reduction, the effect of CP on the reduction of the brakes. We don't have time to get into the detail of the equation and the parameters and assumption that goes into it, but one thing that I just want to mention here is the transition period that was considered subsequent to the CP installation. As you see in this graph on the right, after installation, pipe is going to age, and the number of brakes increases as the pipe ages. But then after application of CP, there is going to be a transition phase or transition period before we see a significant reduction in the overall brakes. And after CP, the pipe will continue aging, but at a lower rate. And we call that the post-retrofit slow aging process. So what is the reason for considering a transition period for CP? The reason is that before installation of a cathodic protection, an existing pipe may already be corroded and has a significant wall loss, and there is some imminent breakage. So the cathodic protection may delay those breaks, but may not completely prevent them. So if there are already significant amount of corrosion at some areas, those breaks are going to happen, and cathodic protection cannot undo it. But it's just going to happen at a slower rate. And also, as we are adding anodes and increasing our coverage, it would take some time, and that also is considered in the transition period. So using this approach and the equations and assumptions and the parameters that were described in our Chapter 8, we created various scenarios and financial models, and of course, all of them have charts and tabulated summaries. We are hoping that this is helpful for utilities in order to look at the different scenarios and find a case that is similar to their system and use these scenarios to make decisions. There are the various scenarios considered various conditions with retrofit, keyholing, and joint bonding in low corrosive soil versus high corrosive soil with a varying cost of the brake. When we're talking about the brake cost, I typically refer to excavation cost. You see a snapshot of those graphs, and of course with each graph there is a tabulated summary that goes with it. So what was the conclusion from our financial models? The financial models included that hot spotting is a no-brainer. Any type of CP will result in a lower cost than pipe replacement. A delayed retrofit has higher cost in corrosive soil, but is still better than the replacement. For existing pipe in low corrosivity soil, retrofit at the first sign of increasing failures. And more importantly, hot spotting is effective for protection of pipelines smaller than 32 inches and is a good starting point, especially in a small water department with limited resources, as an interim program as a retrofit is being planned. So now we get to the my favorite part of the report, which is the best practice manual. And I think it would be very useful for utilities. Before we discuss the best practice manual, if you are among the utilities that currently do not have any cathodic protection program and you're wondering where to start, I would certainly recommend that you review Chapter 4. This chapter discusses the utility decision framework for implication of cathodic protection and opens up the different deciding factors such as feasibility, CP program and asset management, designing policies, asset performance CP, and financial CP and monitoring. It opens up these discussions and provide examples for each case from different utilities. A very important point out of all these factors is that in order to really justify the cost of CP and assess the performance of CP, we certainly recommend that you start collecting data, break data, even before you start your CP program. That will be very helpful in justifying the cost and seeing the effectiveness of the CP. For financing CP program, as we briefly mentioned earlier, for new pipelines, the financing should come from the CP program financing should come from the source that the new pipeline is coming from. But for anode retrofit, typically it can be justified as capital improvement cost, and for hot spotting, which can be part of a routine maintenance, it can come from the O&M cost. Okay, now we get to the best practice manual, and this best practice manual in Chapter 9 is a guideline but not a roadmap to assist utilities in developing their own best practice manuals. As a utility, you may decide to increase or decrease the level of complexity, and I personally think that this guideline is very helpful in discussing with water utilities executive manager to consider CP as a cost-saving alternative for maintaining the level of service. The best practice manual also describes the framework to asset management and planning authorities, and of course it's a value-added program, and it's not intended to create large construction, and it's not to be used as a specification for engineering design of CP. So when it gets to the system, critical system, where failures may cause significant damage to the system, shutdown, or endanger human life, we still recommend you to go with the expert design, and this cathodic protection should be designed by a qualified engineer or NACE International Cathodic Protection Specialist. With that, I want to show you a snapshot of the best practice manual that we have in Chapter 9. It is written in a very simplified specification kind of format that is bulletized, easy to read. It's down to the point, and even if you are not a big fan of writing too much text, at the end of each section, we have a boxing green text that highlights the most important items that you need to know in regards to the CP program and the guidelines. So I would certainly recommend that you take a look at this, and it's going to be, we feel that it's very, very utility friendly, and it's going to be helpful. So with that, a quick summary of Water Research Foundation 4618. So the key aspect was to take action instead of accepting the historical view of inevitability of corrosion in water systems. Hot spotting is a no-brainer and is a perfect for any kind of breaks and repairs when corrosion has become influenced on the failure. Hot spotting is typically effective for protection of pipelines smaller than 32 inches and is a good starting point, especially in a small water department with limited resources and as an intern to the retrofit program is being planned. Hot spotting can stabilize the annual breakage rate in a short-term situation and can reduce the overall breakage rate over a long run for pipelines with no CP. Retrofit cathodic protection is the best choice on existing pipe where the joint points were not installed at the time of pipe installation, and breakage rates are starting to increase beyond the utility accepted range. CP retrofit would extend the life and should be installed as soon as the corrosive break patterns are identified. The best practice manual developed as part of this project provides a framework for CP retrofit program. The manual is intended to be used as a guideline, not as a roadmap to assist utilities in developing their own best practice manuals. The case studies conclude that among all the utilities studied, no one-size-fits-all exists in the CP program. With the variation in pipe characteristics, materials, soil, environment, and other risk factors, a customized approaches are needed. And with that, I just want to thank you for your time and turn it back to Dr. Zhang for Q&A. Thank you.
Thank you, Mercedes. Now it's Q&A. So we have received many questions. I think some people ask as to where they can get a report or the manual. The manual is a part of the report. So at the beginning of this webcast, I showed a link where you guys can download this report. and to try to use this manual. Let's see the questions here. So the first question is, did you also check water conditioners with zinc sacrificial anode performance?
No, because we're looking at the outside of the pipe, which is the water conditioners don't involve the outside of the pipe. This is external corrosion.
All right, thank you. So what are the CP recommendations for new ductile iron pipe installations?
Well, so this was really addressing existing iron pipe. If you go back to the 2004 2608 project, we talked about ductile iron pipe in great sort of detail, and it's included in the corrosion control master plan. Things have changed a little bit since then, because now there is the option for zinc coating on the outside of ductile iron pipe. And while we think that is certainly valuable, it doesn't replace the need for cathodic protection. In general, we've always had the view that you need to prepare for cathodic protection even if you don't apply it from day one. So for ductile iron pipe, we've always recommended that you bond the joints so that you can always put cathodic protection on it. And the next step is to encase it in a polyethylene wrap. I know some people don't like polyethylene wrap with cathodic protection, but our experience has been it works. The third thing is to install test stations, and those test stations allow you to apply cathodic protection easier in the future. These are all prophylactic things that if you have a pipe that starts having corrosion problems in the future, by having bonded joints, by having some kind of a wrap on the outside of the pipe, and by having facilities to apply current to, you've made your life in the future, or probably the next generation of engineers behind you, lives a lot easier, which is very common in the water industry. If you think about how many pipelines are built that have side outlets that are for future connections. The water industry has a long history of making plans for the future. The only exception really is in the application of cathodic protection. So I guess it's always bond, always coat or encase, and put the facilities on you need to apply cathodic protection, so it's a lot easier for you when you have to do it in the future.
Great, thank you, Graham. This new question, I think you answered some of it. So the question is, do the conclusions change whether it's a ductile iron pipe versus steel? And what about pipe greater than 32 inches?
We don't. This is mainly focused on distribution piping. Existing distribution piping is really meant for smaller diameter pipe. With larger diameter pipe, what happens is if you have as many leaks on a large diameter pipe, you'll be replacing it long before you ever have that many problems. So the good example is the average leak rate on our leak or break rate on distribution piping is about 20 leaks or breaks per 100 miles per year, but that's for small diameter pipes where leak repair is common. Taking an agency, a transmission agency like San Diego County or Metropolitan Water Southern California, they have a few hundred miles of pipe, but if they had 20 leaks per year on the large diameter pipe, there'd be a lot of people out of jobs. So yes, it does change how you approach it. The focus of this particular project was on distribution piping.
Thank you. So Mercedes, does the manual include details for impressed current systems?
So no, the answer is no, because the focus of this report was hotspotting and retrofitting, which is part of the galvanic system. However, we do briefly mention about the impressed current system, but we don't get into the details of it.
Thank you. And is it recommended that water utilities analyze the soil resistivity in order to locate the potential problem areas for pipe corrosion?
Resistivity is only one measure of what causes problems on pipes. It is certainly one way to classify the corrosion, corrosivity of the soil. Probably of more importance on distribution piping is our connections to services and grounding systems through those services. Most services are copper, and the copper service into a cast or ductile iron main creates a galvanic cell, and defeating that galvanic cell, it will do more. You're more likely to have galvanic cell corrosion, which will be mitigated by the application of cathodic protection also. So understanding where your galvanic cells are, understanding why you're having corrosion leaks is really important. Corrosivity is only one part of that. So I never want to say no to that, but there are other ways that you can understand what kind of corrosion you're having and where it is, and understanding the problem is the first step to fixing it.
Great. The next question is, how do you determine what area gets a CP retrofit versus replacement?
Well, so that's a good sort of question. So there's an economic analysis that you have to do depending on where it is and what the accessibility is. And there are lots of programs out there that will go in and look at break rates and replacement costs and give you the financial payback for that. In general, where you can't stand extreme surface disruption such as open cut excavation, cathodic protection extends the life of a pipe. It can't put the material back. I always go back to Glenn and Zelch from Louisville Water Company, who, when I was doing the project back in 2004, he had developed what he called the 2 + 2 + 2 rule, which was if you had 2 breaks within 2 years within 2 blocks, he replaced that section of 2 blocks. And so it comes down to the finances of it, and that's really an individual utility discussion, and it's hard to have a general discussion, but those are some of the ways you can do it.
So basically, if you meet that rule, 2 by 2 by 2 rule, that's a state of disrepair that CP will not be helpful.
No, it still will help, but that was his rule. And eventually they went to hotspot. I think they went to hotspot protection as well as retrofit. They had a very sophisticated program that looked at that from an asset management standpoint, took into account their own understanding and tolerance for risk. So what I'm saying is that it is an individual utility decision. It is not a general. There's no general rule. So it depends on each utility.
Thanks, Grant. So Mercedes, here's another question for you. Can you elaborate further on the slide that showed the cost for corrosive soils versus non-corrosive soils? It was not clear what that meant.
Yes, so in that slide, we were talking about the different scenarios. So we did our financial modeling at different scenarios with different pipe conditions, and considering if the pipe happened to be in a corrosive soil versus non-corrosive soil or low corrosive soil. So if you go back and read the chapter, you would see that sometimes, for example, if you were going to install the retrofit at, at age of 0 or at the installation time for a pipe that is in a low corrosive soil, then maybe you could wait a little bit longer. But when you go in a highly corrosive soil, you should consider installing CP from the beginning. So that's why it's just a parameter that changes the scenario and result in a different conclusion for that scenario. So there are over, I believe, 25 to 30 different scenarios with different parameters, varying parameters. So if you go back and look at your system and compare it to one of those scenarios, maybe you can find a good match and use that kind of scenario for your projection.
Great, thank you. So do you know what vendors supply the anodes?
Say that again.
So what vendors supply the anodes?
Oh, there are local and national. So, the anodes are supplied by Aegion, with Corpro Aegion, Far West Corrosion in the west, Mesa Products, and there's other local ones. But there's always a local vendor, and then there are some national vendors.
Thank you. So the next question is there a method of mechanically attaching the anode wire to a pipe during hotspot application, or is the spark weld the only option?
Well, we prefer hardwired connections where you get a welded connection. Mechanical connections underground do not have a very robust history of staying and maintaining their connection over time. If your concern is the amount of sparks and fury that occurs with a CAD weld, pin brazing is a technology which has come in of its own, which is much less exciting than CAD welding, but it generally it results in a metal-to-metal contact. So pin brazing would be the next best, which does end up with a mechanical stud on it, and you have to protect that stud. But we really don't prefer that. CAD welding is the best way to make sure you have a good connection.
Thanks. So since you started this project, did you notice any increased interest in CP? If not, what might be done to promote it more widely?
Yeah, so there's been more interest in it. I also think that the industry is more open to it with the movement towards asset management, and in some ways that the recession or the downturn helped is that people had to do more with less, so they begin to look at life extension versus replacement. So yes, we have seen an increase, much better response to this report than our previous report in 2004.
Thank you, Graham. The next question is, you mentioned that hotspot CP might not work too well if it's not designed or planned. So how would you go about making up a systematic plan for hotspot installation?
So, hotspotting is not meant to be perfection. It's meant to first do no harm. And so what you typically do from a systematic standpoint is you assume you take a standard size anode, say a 32-pound magnesium anode, and the point is every time you have an excavation to do a leak repair, you install that anode at that location where you had the leak. It is not perfection. It's a Band-Aid on a wound. It's meant to do something rather than not do anything. If you don't do anything, the guarantee is that things will get worse. So hotspotting is not a perfect science. It is not really a designed solution. It is a very simple way of of doing yourself some good without having to go through a capital project. and taking advantage of the hole you already have in the ground.
Great answer. So I think we have time for the last question. So the last question is, on existing pipelines, do you recommend retrofitting with impressed current systems?
It all depends on the electrical properties of it. If it doesn't have intentional electrical continuity, then you have to go back and make it intentional electrically continuous. And that means digging up or accessing every joint internally and creating a bonding along it. So the biggest problem as identified in the 2608 project is that we have all this existing not electrically continuous pipe in the ground, which makes the application of cathodic protection using impressed current very, very hard. Impressed current has the advantage that you're able to protect larger structures with more current, but the caveat is you have to have electrical continuity at the joints so that you don't create self-corrosion. So it's one of those things. If you have electrical continuity, if you made those plans that I talked about at the beginning, where I talked about, having electrical continuity, making electric continuity, then you have a much easier job ahead of you.
Great, thank you. So I think this is all for today. I want to thank our speakers for the excellent presentations and our audience for the great questions. Thank you for attending the webcast. Don't forget to take the post-event survey. Let us know how you think about today's webcast. Thank you.